Today I'm going to talk about shear testing of pre-stressed concrete bridge girders. And at this point, I would like to acknowledge the other researchers involved with this analysis and with this testing, our PhD students Gabriela Zarate and Fengxiao Zhang, our postdoc Minkuk Park, and my colleague Dr. Yu Guangyang. So here's an outline of my presentation for today. I'm first going to give an introduction on this testing and the need for this testing. Then I'll give you some of the results of the experiments and recommendations for practice, and finally summary and conclusions. So the reason why we are interested in testing these type of girders is that we are working on the assessment of pre-stressed concrete girder bridges. There's about 70 pre-stressed concrete girder bridges in the Netherlands. These are bridges that have thin slabs cast in between the girders, and the whole system is kept together with transverse pre-stressing. So we call this slab between girder bridges. So most commonly is the slab on girder bridge, where you have the girders and then the deck slab on top. This structural system is slab between the top flanges of the girders. We also have a number of diaphragm beams that also make the system work together. Now, in the past, we focused for assessment on the capacity of the slabs, because these are very thin slabs, and according to the first evaluations, we found that their punching capacity was insufficient. Now, previous research has shown that in these cases, compressive membrane action causes that the capacity is much larger than what we would find from the code equations, and that this mechanism does not break down under fatigue testing. So we actually could conclude after a lot of testing that the slabs are not the governing members. What is governing for assessment now are the pre-stressed concrete girders, which have a unity check larger than 1 for shear tension, for the failure mode of shear tension. And the unity check in the Netherlands is used instead of a rating factor. A unity check is load effects over capacity. So if it's larger than 1, it does not fulfill the code requirements. Here you see one of these slab between girder bridges under construction in 1965. I mentioned that in Delft we've done a fair amount of research on the capacity of the decks. So here you see the test setup that was used to test the punching capacity of the decks. That was the PhD research of Sana Amir. You have the reference here on the bottom. So as I said, now upon assessment, we find that it is the pre-stressed girders that are governing for shear tension. So let me introduce you the specimens that we tested. These specimens are taken from a demolished slab between girder bridge, the helper zone bridge. This bridge had to be demolished because of the redesign of the perimeter around the city of Groningen. And since these are actual bridge girders, they have all the details that real girders have, and that not all typical laboratory specimens have, such as the parabolic tendon profile, with some of the tendons even anchored in the top flange. We have all the way at the end here, we have the anchor part, and then we have a part where the cross-section, the width of the cross-section tapers towards this part here where we start to have the thin web. Now, as I said, we tested the full girders, but they were sawn in the field in half so that we would be able to handle these in the lab. So the actual length of the girders in the field is about 25 meters. They were sawn in half, so we ended up with specimens that were between 10.51 and 12.88 meters in length. And the overall height, cross-sectional height of the girder is 1.11 meters. We tested 4 of these specimens at two different positions of the concentrated load at 2.9 meters from the support and at 4.4 meters from the support. So 4 experiments on 4 different girders. Here you can see the 4 girders that were taken from the bridge. So this is a cross section of the slab between girder bridge. So you see how the slab is indeed cast between the top flanges of the girder. And here you see the tendon profile. So as I mentioned, the number of tendons, this is a special detail, but the number of the tendons, tendon 1, 2, and 3, are anchored in the top flange. So that's quite a special tendon layout. And you see here all the other tendons and their position. You also see that there is very low stirrup reinforcement. There's a diameter 10 millimeters at 400 millimeters on center. And let's have a look at 2 of the cross sections, AA closer to the support and BB at the center line. So these are the cross sections that we're looking at here. So at BB, as expected already from the previous drawing, we have all the tendons in the bottom flange. Whereas in AA, we have the position of the tendons here based on the tendon profile. Now, the goal of this research was to look at the shear tension capacity of these girders and really to evaluate, is shear tension the governing failure mode in these girders? To use these experiments to compare to nonlinear finite element analyses, and especially nonlinear models that have been developed with the Dutch guidelines for assessment using nonlinear finite element models. We have in the Netherlands a guideline for using nonlinear models, but these have been developed for slabs, reinforced concrete beams, as well as pre-stressed concrete girders. But of course, these special girders present a case that have not been used for validation yet. And if I go back one slide, you can see the shape of the stirrup follows the shape of the cross section. That's not allowed nowadays anymore because we think that underloading the angle here of the stirrup will try to open, and that this part is going to fall off. So we also wanted to evaluate if that's really a failure mode that happens, or if these non-code compliant stirrups still function in carrying load. So here is our test setup. What you can see is the girder and the frame and the jack that we used, side view and front view. And this is a photograph of it. So we've used a large frame. That's the frame that we use in the Steven 2 laboratory for all large-scale testing, with the 2000 kilonewton jack, and for the last experiment we used our 5000 kilonewton jack. Some details of the test support. Here you see the detail of the support, and here, since the specimens were sawn, we wanted to avoid the pre-stressing tendons to pull in and cause a splitting failure on the sawn edge. So we provided vertical pre-stressing. So these are Diewiedach pre-stressing bars to apply an actual load on the cross section to avoid that failure on that side. In terms of instrumentation, we have applied a regular set of LVDT measurements to find our strains in a grid on the side. We've applied laser distance finders to find the deflections. We've used acoustic emission sensors to study the wave-based properties. We've applied as well smart aggregates and cast them into the specimen. And we've taken photographs to do an analysis using digital image correlation. So here you see an example of a smart aggregate. It's essentially a piezo resistant layer between 2 marble layers. here is the sensor plan for one of the experiments. It varied a little bit among the experiments, but gives you an idea. We have the grid of LVDTs to find the strains and deformations. We have the positions of the acoustic emission measurements, 15 in total. We have the laser distance finders under the position of the load. And then we have, well, it's not shown here, but on the other side of the specimen, we have the speckle pattern, and we take photographs to do the digital image correlation. We've done material testing to find the stress-strain relationships of the pre-stressing steel and the mild steel. And we did core testing to find the concrete compressive strength. So we know that we are dealing with a European concrete class C5567. So that's a 55 megapascal characteristic strength when testing on cylinders, and 67 characteristic compressive strength when testing on cubes. We tested the pre-stressing steel. So here you can see the results of testing the pre-stressing steel coupons that we tested to find the stress strain diagram. And we also tested the mild steel. The mild steel were plain bars, and we found that it had an average yield strength of 454 megapascal, so we could identify it as a QR, or it was shown on the drawings to be an old Dutch QR40, so a mild steel with design strength 400 megapascal. Of a characteristic yield strength of 400 megapascal, I should say. And we found an average yield strength of 454 megapascal, so a little higher than we expected. We expected 440. We also wanted to have an idea of the pre-stressing level in the girder after all the losses, and we looked at a number of methods. First of all, we looked at the traditional method using just a cracking moment. Then we looked at a more advanced analysis using a full sectional analysis, both using a layered sectional model that Min Cook programmed, as well as validating this model with Response 2000. And then we also measured, we tried to measure this by first drilling cores and seeing what would be the strain release in the concrete. And we did that by measuring with an LVDT as well as with the digital image correlation. And we also did the destructive method of cutting through the tendon and just measuring the difference in strain as the tendon is released. For the third girder, we found with cutting of the wire that we had quite some, you see, we cut 4 wires, and we had quite some difference on the results, right? You see that they range between 66% and 121%. And essentially with all the measurement techniques that we use to define the pre-stressing level, we found a large variation on the results. We actually found that using the sectional analysis was seemed to be a more reliable method. But so we found here that we had an average of 107% of the pre-stressing level that we would calculate based on the Dutch guidelines for the assessment of existing bridges, where we have a method to estimate the remaining pre-stressing level in an existing girder. In terms of loading, we used a loading protocol with loading to different levels and unloading, so that we could follow the opening and closing of cracks, and we could use this for determining the wave-based properties. Here's an overview of the results of the 4 experiments. You can see that they've been tested between June 2019 and December 2019 with the properties of the geometry. A over D distances are outside of the the region where we consider typically a direct compressive strut to develop between the load and the support, but our results have shown that there was the development of a compressive strut even at the larger A over D distances. Here you can find the values of the externally applied load for which we had the first flexural crack with F cracking, the first shear crack with F sub shear crack, the first shear tension crack in the web with F shear tension crack, and then the maximum load with F maximum, and also the associated deflection. And the failure modes that we observed were a combination of shear compression failure with some with opening of a flexural shear crack in the first two experiments. In the third experiment, we saw local crushing of the concrete in the top flange, as well as shear compression failure. And in the last experiment, we had as well crushing of the compression field. Here's the last experiment, or the recording of the last experiment. You can see that here we are using a larger jack. Since in helper zone 3, we had a maximum load that was very close to the 2000 kilonewton capacity. In this case, we used the 5000 kilonewton jack. So as you can see, a brittle shear failure. Here's a video of some of the post-processing that we did based on the on the photographs that we used, that we then processed with digital image correlation. So you can see how the cracks develop. So you see first the flexure cracks, then the flexure shear crack, and then the development of the crack in the web along the shear tension crack or the web shear crack. Here are some further results of the digital image correlation. So we developed this, or I should say Gabriela developed this over the course of the experiments, but essentially we've been able to calculate the crack opening and sliding. And of course, crack opening and sliding are important input parameters to actually be able to calculate the aggregate interlock on the crack. So with that, we can estimate which part of the shear is carried by aggregate interlock. When it comes to acoustic emission monitoring, some things that you can see here is based on the analysis of the results is when we have our first bending crack, we really see here hits in the part that indicate that that flexure crack, and you see that here based on the post-processing as well. Whereas in this part, we really see the hits in the web, indicating the shear crack, and this relates as well to the load at which we started to see shear cracking. When it comes to comparing our results to predicted capacity, we looked at inclined cracking load as well as ultimate load. So let's first look at the inclined cracking load for shear tension and the inclined cracking load for flexure shear cracking. So what we've done here is calculated this sectional shear with the different methods at different cross sections and compare this to the sectional shear at which we observed that cracking. So we have here the results using the Euler-Bernoulli method, the Eurocode formula, and V sub CW from the ACI. This is for experiment helper zone 2. And this is for the flexure shear cracking, where we have the capacity according to the Dutch RBK, the method for assessment of existing bridges. The RBK method, where we replace the stress from pre-stressing with the stress at the decompression moment, and the V sub CI from the Eurocode. One thing that we studied further is the influence of the pre-stressing level. So as I mentioned, we looked at a detailed sectional analysis to actually find or to fine-tune the value of the pre-stressing level in the tendons based on the stiffness and the moment of cracking here. That was not just based on the sectional shear force versus deflection graphs, but also really zooming in and seeing where the stiffness changes and what we can analyze from a sectional analysis there. Now, if we compare our results, we can see then the failure mode changes as we change the position of the load. In all cases, we first had shear cracking and then could further develop the strength. But for loads closer to the support with A 2,903 millimeters, we had clear shear compression failures, whereas for larger in the field at A 4,400 millimeters, we had either local crushing in the concrete compression zone or crushing of the concrete compressive field. One thing that we've been able to analyze further with the digital image correlation analysis is the angle of the compression field. So here you see some of the analysis that is done. And on this graph, you see the angle of the compression field as a function of time. And here, for comparison, you see the loading graph. So this is really after all the cycles of loading, this is until failure. And what we see really is how the angle rotates downwards, right? We start at 45 degrees and then it rotates downward and downward and downward until we are at about 22 degrees. We've also learned from our measurements that the acoustic emission measurements can capture cracking early before any of the other methods. That we can have an insight in the shear carrying mechanisms by using digital image correlation, and in particular, the analysis with aggregate interlock. We've been able to look and to actually confirm how the compression field rotates further downward. And we also learned that if we want to measure the displacement under the load, we need a sufficient range with the laser distance finders. Now, if we want to apply this to load testing of pre-stressed concrete girder bridges, this is a topic that is still ongoing research. We've done a collapse test on a bridge of this type in 2016, and we are planning to relate the insights from our research in the lab to collapse testing. With regard to some recommendations for practice, we found that for the assessment, there's a few other topics that need to be addressed if we really look at slab between girder bridges, and those are system behavior and transverse flexural distribution. These topics are being studied by Sebastian Ensling, one of our PhD students. We also found that, as I said, in the Netherlands, there's this Dutch guideline for nonlinear finite element analysis, the RTD 1016 from 2017, which is, if you follow the guideline, we get good predictions of the experiments, and so that could be used for assessments. And one of our master students was looking at the draft new Eurocode, and he found that there were some promising results when using the draft new Eurocode as well as Response 2000. We are at the very end of analyzing the test results. We still need to work on the assessment or outlining assessment method for these types of girders. And we want to use the insights from the different monitoring techniques for short-term field testing, load testing, or as well as long-term monitoring. So to summarize and conclude, we carried out 4 experiments on pre-stressed concrete girders filling in shear. All failure modes were related to concrete crushing, either crushing as in shear compression, so losing the compressive capacity in the strut, or local crushing under the in the compression zone, or crushing in the compression field. We seen that we could increase the shear capacity past the inclined cracking load, which indicates that the non-code compliant stirrups can carry load and function as regular stirrups. We looked at a number of monitoring techniques, including acoustic emissions, smart aggregates, digital image correlation in combination with traditional measurement techniques of LVDTs and laser distance finders. And as future work, we have the assessment of pre-stressed concrete girder bridges and using these insights to develop recommendations for field testing of PC girder bridges. That concludes my presentation for today.